All right, so this first section, I want to teach you about ratios, proportions, and something called the geometric mean. We'll start with ratios. This belongs to my son. It's a model of a Lamborghini Urus. On the bottom, it actually has a ratio on it. If you can see that, it says 1/38, which is just the scale factor. It means that for every, let's say, 1 inch on this model, the actual Lamborghini Urus would have 38 inches. Like if that tire were 1 inch wide, then the tire on a Lamborghini Urus would be 38 inches wide. Ratios can be written in 3 ways. We can write them as fractions. We can write them with a colon in the middle, and that's read 1/38. Or you can actually write the ratio 1/38. A little example I want to do with you is the population between North Dakota and Minnesota. If we want to compare those, maybe we would compare them Minnesota to North Dakota. If I were going to do that, I would write out the ratio of the Minnesota population to the North Dakota population. Now, if I were simplifying this ratio, it's the same thing as simplifying a fraction. I would divide the top and bottom by, it looks like 10,000 to start. Those are both divisible by 4. And so my ratio of residents in Minnesota to North Dakota is 141 to 19. I could write that as 141 to 19 or 141 to 19. Now I was just curious, so I actually typed in 141 divided by 19, and that comes out to 7.42. So some people might even write this ratio as 7.42 to 1, which is kind of nice because then you can say for every 7.42 Minnesota residents, there is 1 North Dakota resident. But when they ask you to simplify a ratio, they're just looking for you to reduce that fraction. This next example is another comparison between the height of a baby and the height of its mom. The giraffe is 70 inches tall when it's born, but mom is 18 feet. So let's compare those two. It doesn't matter if we put the bigger number on top or bottom. That's your choice unless they say. So I want to compare the height of that baby to the height of the mom. Now that is a ratio, but it's definitely not a simplified ratio. The first thing I see is that the units aren't even the same. So let's convert those both to the same units. I find it's usually easiest to change the larger unit into the smaller unit. So 18 feet times 12 will give me how many inches tall the mom is. And that's important to do because now the units actually cancel out, and we're just comparing the 70 to the 216. And that doesn't have a unit other than its length. So if I measured something on the giraffe that was 70 millimeters, maybe from ear to ear, then I could expect that on the mother, from ear to ear would be 216 millimeters. When you reduce a ratio, when you simplify a ratio, there's no longer a unit involved. I still want to simplify that all the way, so divide by 2 on the top and the bottom, we have 35 to 108. 35 to 108. 35 to 108. 3 ways of writing the ratio of the height of the baby to the height of the mom. Let's solve a couple of problems here. The area of a rectangle is 72 square inches. The ratio of the length to width is 2 to 1. What are the dimensions of the rectangle? So the length being 2 to 1, that just means that maybe if this were 10 inches, this would be 5 inches. Because if you reduce 10 over 5, it's 2 over 1. But remember that it says that the area is supposed to be 72 square inches, and a 10 by 5 would be only 50 square inches. So let's try again. Maybe it was 16 and 8. That would be a 2 to 1 ratio, and 16 times 8 is 128, so that's too big. Now instead of continuing to guess and check, I'm going to show you just a little trick. 2 to 1 is the ratio, so if I called this longer length 2x and the shorter length 1x, that would automatically be in a 2 to 1 ratio. And what I've been checking every time is if I multiply those two dimensions together, does it equal the 72 square inch area? So let's solve that equation. I can do the 2 times 1, which is 2, and the x times x is x squared. Divide both sides by 2. Take a square root. And I get plus or minus 6. I'll use the positive version. That means that I'm going to take 2 times 6, which is 12, and 1 times 6, which is 6, and it turns out that 12 by 6 not only fits that 2 to 1 ratio, but 12 times 6 is 72 square units. So we don't have to guess and check if we play it smart. This next example, the measure of the angles in a triangle are an extended ratio of 1 to 11 to 24, an extended ratio. So that's comparing 3 numbers. What are the measures of the angles? Well, we could consider, this definitely isn't a scale, that one is 1 degree, the other angle is 11 degrees, and the other one is 24 degrees. But that wouldn't make sense because those don't add up to 180. What if we double them? 2 degrees, 22 degrees, 48 degrees. That still doesn't add up to 180. But if 1 to 11 to 24 is the extended ratio, why don't we just call them 1x degrees, 11x degrees, and 24x degrees? And what have I been checking? I've been checking to see if those add up to 180. If I combine my like terms here and solve, I find out that my scale factor is 5, which means if I take that extended ratio and multiply by 5, I'll have those 3 angle measures. So 1 times 5 is 5 degrees, 11 times 5, 55 degrees, and 24 times 5, 120 degrees, and 5 plus 55 plus 120 is 180, and is also in a 1 to 11 to 24 extended ratio. Let's talk proportions. A proportion is just an equation that relates to ratios. I've got an example here for you. This is Ronald Reagan made out of jelly beans. Apparently he was a big jelly bean fan, and the Jelly Belly company even sent him regular shipments at the White House. So somebody made this portrait of him out of jelly beans, like a mosaic. It's 48 by 48 inches, 4 by 4 feet. It's huge. Don't you wonder how many jelly beans would be in that entire portrait? Well, I didn't want to zoom in and count all of them, so what I did is I just zoomed in on one little part. I think it was this part right by his tie here. Now that was only a 4 by 6 inch rectangle, but it had 98 jelly beans that I counted. So I could look at a ratio of the jelly beans per square inch on that little section I picked out, and that ratio should be equal to the jelly bean to square inch ratio on the entire portrait. So my jelly bean to square inch ratio on this little section is 98 jelly beans. 6 times 4 is 24 per 24 square inches. So that's just a ratio. And the ratio on the big portrait, well, I don't know how many jelly beans there are, but 48 times 48 is 2,304 square inches. And what I was saying is that the ratio of jelly beans to square inch should be the same for both of them. They're from the same picture. And that's where we get a proportion. A proportion is just 2 ratios that are equal to one another. And I made sure I was comparing jelly bean to square inches to jelly bean to square inches. So now I just have to solve this equation. A little algebra throwback here. The opposite of dividing by 2304 is multiplying by 2304. And on the other side, the opposite of dividing by 24 is multiplying by 24. And that's where we get the idea of cross multiplying. If we take both sides by 24, the x gets multiplied by 24, and the 98 gets multiplied by the 2304. And then we don't have those fractions anymore. And I get 9,408. Remember that that was the top number, which represented jelly beans. So that's how many jelly beans are in that entire 4 by 4 foot portrait. Now that's just an estimate, but I think it's pretty close because shouldn't those ratios be equal? That's why I can use a proportion to solve. I just wanted to practice a little bit more of that algebra with you. So cross multiplying, if I multiply both sides by 15 and I multiply both sides by 5, I'll get the 4 times the 15 and the x times the 5 Divide both sides by 5 and I get 12. Always a good idea to check that in the original equation. But one thing I noticed was, did you see that 5 times 3 would give us 15? And 4 times 3 would give us 12. So I'm pretty confident that 12 is going to work. So that's almost a shortcut, right? 5 times 4 gives me 20. So 8 times 4 would give me 32 for y. Can't really do that on the next one because 1 times 3 would give me 3, but what's that bottom part times 3 going to give me? That doesn't even help. So let's go back to that cross multiplying method. I'll take the 3 times the x minus 6 and the 1 times the x. Distributing the 3, 1 times x is x. I need to get my x's on the same side. I think I'll subtract 3x from both sides. And then divide by -2 and I get 9. Let's check that out. 3 over 9 compared to 1 over 9 minus 6. Yes, those are equal ratios. 3 over 9 and 1 over 3 are both 1/3. One more just for practice. 3 times m plus 1 and 2 times m plus 5. Remember that those are always set equal to one another. This doesn't stop being an equation. We'll distribute. Maybe subtract 2m and subtract 3. Let's check that out. 3 over 7 plus 5 and 2 over 7 plus 1. 3 to 12 and 2 to 8 are both 1 to 4, so that should work. The last thing I promised you was to teach you the geometric mean. We've heard this word mean before. It means average, right? So if you were to find the mean of 2 and 8, wouldn't you just take 2 plus 8 and divide by 2, since there's two numbers? 10 divided by 2 is 5, and we would say that the mean is 5. Now that's not a geometric mean. That's actually something called the arithmetic mean. And the arithmetic mean was really useful when we were looking for midpoints, right? Because those are equally spaced. 2 plus 3 is 5, and 5 plus 3 is 8. So 5 is right in the middle. Now the geometric mean is actually based on multiplication instead of addition. So you can think about a number line still, but it wouldn't be equally spaced addition-wise, but multiplication-wise. And the geometric mean not calculated by adding and dividing by 2, but instead by multiplying and, instead of dividing by 2, taking the 2th root, the square root. In this case, that's the square root of 16, which is 4. So we would say the geometric mean of 2 and 8 is 4, which isn't equally spaced position-wise, but multiplication-wise it is. Do you see how 2 times 2 would be 4? And if I multiply by another 2, I'd get to 8. So multiplication-wise, 4 is in the middle. Again, the geometric mean, you just take the two numbers, multiply them, and take a square root. Let's try one more. The geometric mean of 10 and 50. 10 times 50. The square root of that, the square root of 500, which comes out to about 22.36. And that's the geometric mean. 22.36 would put us right about here. And in this case, it turns out that our multiplier for the geometric mean is 2.236 approximately. So try taking 22.36 times 2.236. We get 49.997. That is darn close, just because of rounding. But that's the idea of a geometric mean, is that it's equally spaced by multiplication. And it turns out that the geometric mean does pop up in geometry relationships. We'll see that more this chapter.